To open today's event, please welcome Professor John Kelleher. He's the Chair of Computer Science at Trinity College Dublin and Director of the ADAPT Centre. Welcome.
Thanks, man. Oh, is that one working?
Yeah, it is, yeah, you can take it either.
Thanks very much. How are we doing, everybody? So it's great to be here this morning, and I'm delighted that you're all here with us. I'm delighted to welcome you to Trinity. It's a gorgeous room, and I think it's a great venue for what we're setting out for on today. To give you a little bit of background of who I am, so I'm the director of the ADAPT Centre, and the ADAPT Centre is a Research Ireland centre for digital content and AI-driven technology. It's a partnership across 8 universities across Ireland. We have about 450 members. That's between faculty, PhDs, postdocs, and researchers. We're working across all of the AI space, from developing new technologies through to governance and human-computer interaction and workflows and regulation and standards. And we are very keen, well, in fact, we are designed and set up to not only work in fundamental research, but also to engage with industry. And that's why today is such an exciting morning for us. Working with Ergo has been around for 32 years, I believe. So it's just a little bit older than I am in terms of my AI career. And it's an Indigenous Irish company that's grown to a global reach. And it's really exciting for us to be working with an Indigenous Irish company. It's part of what Research Ireland wants us to do to support Ireland to have a global impact. And that's why Ergo is a perfect partner for us. So I'm delighted to have this opportunity to work with Ergo this morning, and looking forward to working more in the future. I think my task this morning as the opening speaker is to try and demystify AI to set the stage for the discussions we're going to have later on. In large part, what I'm going to try and do is there's a range of terms that are floating around, and I want to try and clarify the meanings of those terms and put them in context in relation to each other. So some of the terms that I'll try and cover, I'll try and give a clear explanation of what a large language model is at a slightly deeper level than you might have come across earlier, how they're constructed, the large language model development cycle, things like the difference between what we might call pre-training and fine-tuning, reinforcement learning with human feedback. You might have heard of those things. The difference between what a chatbot is and what a reasoning language model is. Not all language models are the same. And there's a range of other topics we'll come across in that journey. So that's my plan. Hopefully it's interesting for you this morning, and that it gives us a good basis for our future discussions. I know that Lauren later on will talk a bit more about what's happening right now in terms of agentic AI. I know that's a space that Ergo are doing a lot of work on at the moment. The field's moving so fast that having a partner who can help to guide you through the challenges, particularly ones where there's a technology that has risk associated with it, and you need to have good processes around that in terms of governance and data management, is really useful to partner with a trusted company. So, to start our journey this morning, we're really going to start with the basics. So, what is AI and why it's mattering at the moment? So, there's a lot of discussion. So, I've given lectures on artificial intelligence for over 30 years now, and there's lots of questions about what's intelligence, what does it mean, lots of different types of intelligence, etc. But for the purposes for today, we're really talking about systems that can do things that we humans would normally attribute intelligence to in the requirement of completing those tasks. Previously, that would be things like playing chess, but more generally now it's problem solving and reasoning. It's moving forward. And learning is a key part. So AI, by the way, you can trace it back to a particular point in history. So to the 50s, there was a conference that was set up, and you can actually find there's a research proposal written where this group of men, they were all men by the way, wrote a research proposal looking, I think it was for $800 or $1,000 to run a conference for 8 weeks where they'd all come together, and that was the birth of AI. And you can even see what topics they felt was interesting. There was a range of topics in that space, from theorem proving to machine learning to computer vision. It was really drawing on the fields of cybernetics at the time, which is kind of systems with feedback loops in them, early robotics, etc. And early on at the start of artificial intelligence, if you went to conferences, back then and even in the 90s and the early 2000s, there was a lot of variety and differences in the methods used to attract AI. But what's happened over the last while is that the learning component of AI, which has grown into be machine learning and then deep learning, has really taken over and is now dominant. And now, for example, when I was doing natural language processing in the late 90s, early 2000s, natural language processing and machine vision people would have very distinct skill sets, okay, and how they might approach work. Now often though, if you have a machine learning background, that process of creating systems and helping systems to learn by looking for patterns in data goes across all those fields. So the field in some way has homogenized in terms of the methods it's used to create systems. One of the things that's coming forward from that is where we've moved from rule-based systems to these data-driven systems is also that these data-driven systems are more robust than the rule-based systems that were before and the different forms of systems that we had when the field was more disparate. Now what that indicates though is as the technology becomes more robust, it's having a greater impact outside of academia and outside of the lab because it's more usable. And that means, and you'll see today now, that AI and generative AI is now, the genie's out of the bottle, it's being used everywhere. We have kids using it in school. That's a real sign of robustness. They'll find any way to break technology. And that's why it's important, that's why we need these events today. Because it's having such an impact and it's such broad use, it's really transforming a huge number of processes in the world. And it's having a massive impact on workflows within industry. I'm sure you've come across it or you're curious as to how it can impact on your business. Hopefully by the end of the day you might have some strong ideas about that. I know a lot of people are interested in use cases and we'll try and come across some of those and ground those out for you today. A brief history of AI. As I look at these slides, getting to a stage where it doesn't seem like a history, more like a biography. I've been around long enough that I can remember when we were doing a lot of rule-based systems and expert systems. So at the start, when we were trying to create systems that would act intelligently, there was a lot of work where we would speak to domain experts, try to elicit knowledge from them and encode that knowledge manually into rules. There was a distinct shift then over to data-driven systems where machine learning became important. And then you might have heard, or you might have from about 2012 through to 2022, there was a lot of interest in a topic called deep learning. And deep learning is really the foundations for generative AI. So the transition was, let's say, between machine learning and deep learning. Machine learning is the general field of learning from data, learning from samples. And what we're trying to do in that space is, technically, we are inducing a model from data. What does that mean? Well, a model is a computer program that can take inputs and give you an output. And inducing a model from data is we look at a set of examples from data, prior interactions. These could be emails that we've previously labeled as spam or ham, customer interactions, for example, giving out loans, has somebody defaulted, or customers who have left and taken up another subscription. You might be doing a propensity model. And what we're looking at is that set of previous examples. We have an algorithm that looks at that set of examples and extracts a set of rules which are encoded as a program which gives us the model. Okay? And the model will then do the mapping from inputs to outputs. Hopefully that makes sense. So the machine learning process is how do we go from data to a program called a model that will map the inputs to outputs that reflect the patterns that occur in the data and that help us to look at new examples and see which of the patterns we've previously seen is most appropriate for this example and what's the likely outcome given that pattern matching process. So that was machine learning, and there was a range of different machine learning algorithms out there. Within that set of algorithms and families, there was a particular family of model and algorithm which was a neural network. Okay? And that's gone through a number of eras of where it was a hot topic or not. But deep learning really put neural networks at the center of machine learning. Okay? They've gone through a bit of a winter for a few years. And the thing that deep learning allowed us to do was to scale neural networks, to make them bigger. So the thing that had held neural networks back, there was a range of technical problems to do with the maths and how we trained them, that we couldn't make them larger. Okay? And deep learning allowed us to scale the models to make them bigger. And what that did was it unlocked the power of these models to be much more robust and to handle broader data sets. If you bring that forward a little bit, so we had machine learning, deep learning allows us to make neural networks bigger. What generative AI is building on is, if we take the idea of making a very large neural network, which deep learning allows us to do, and we put it together with a standard process called language modeling, okay, which I'll explain to you in a little second, we end up with these large language models like ChatGPT. Now, I've worked with I've worked with language models for a long time, several decades. One of the really surprising things that's happened with generative AI that's made them so important recently is the impact of scaling. Okay, so I mentioned how deep learning allowed us to make neural networks larger. It turns out that when we make them really large, on huge amounts of data, there's some emergent properties that make them very usable and adaptable. The interesting thing about generative AI is it's sometimes also referred to as general AI, because one of the differences is between machine learning and deep learning and generative AI is that in machine learning and deep learning, where you've trained a model, it's typically trained to do one task, and that's the only task it can do. If you need it to change to another task, you have to retrain it. The thing with these large language models is that when you scale them or make them bigger, they're able to adapt to new tasks by you explaining to them in the input prompt what you'd like them to do. And that's where we have this concept of prompt engineering, of figuring out how do we best design our prompts, our inputs to the model, to get that model to adapt to new tasks, to new formats, to new inputs and give us different outputs. And that adaptability is a key part of why generative AI is so important these days. Because one of the challenges we'll all have in businesses is there might be a whole load of people in your companies who are using generative AI in their own way, because they'll find, what way can I adapt this model that best helps me in my job? And one of the challenges is to try and identify the use cases that your company is already using, the people are already using, and try to see which are the most common ones, and can we make a more efficient, scalable process for that? And also, can we govern the process and make it more safer to use? So that's sort of a history of where we've come through, from rule-based systems to data-driven process, and then to scaling to generative systems. Slightly going over it again, what's different here with generative AI versus, if you like, the deep learning processes before. A term that you might have heard alongside with deep learning was a topic called predictive analytics. So predictive analytics was really based around the idea of classifying examples. Okay, I've spoken to you about the idea of looking at examples from history that we've seen previously, identifying patterns, relevant patterns, and encoding those patterns in a program called a model. And that model can then look at a new example and give you an output, okay, that labels that example based on those previous patterns. Okay, in predictive analytics, it could be, for example, that you've got a data set of fruits, apples and oranges, okay, and you've trained a model and it can distinguish between apples and oranges, and then you can show it a new fruit and it can tell you that's an apple or that's an orange. That's predictive analytics, predicting a label for this new example that you've shown it. Okay. I would say sometimes the prediction can be prediction into the future, a sort of forecasting, but other times it's actually just predicting or imputing a missing label for right now. Okay. It's not that that apple or orange is becoming an orange in the future. It's already there. It's just predicting a piece of missing information. Okay. That distinction of classification, of deciding, does this new example belong over here in this category, or this new example belong over here in that category? That is fundamentally in the, I'm going to use a word here, in the representations or feature space that these models use. You need to learn a boundary, okay? A boundary between the two classes, all right? Now, when we come to generative AI, the difference here is, rather than labeling something as being an apple or an orange, we want to be able to generate a new example. We're able to say, give me a sample of data that looks like an apple. Okay? And that's a different task, because instead of learning a boundary between what's an apple and what's an orange, what's differences between apples and oranges, I need to learn the properties of an apple. Okay? And there's actually many more properties of an apple than might be differences from oranges. So it's a fundamentally more difficult task to learn And that's a way of learning the distribution of properties of an apple. Okay? And generative AI, we learn this distribution of the data. And I'll talk to you about what that looks like. And once you learn that distribution, you're then able to sample from that distribution new examples. So that's why in generative systems, unlike in predictive systems where you have a boundary between classes, in generative systems you learn the properties of a particular class, and you can then ask the system, given those properties of the class, give me a typical example of that class. Okay? And you can also, for example, condition that sampling process. So I might be able to say, give me a typical example of that class in this context. So give me a typical example of what an apple looks like when we've had a very hot year, okay, or when we've had a very cold year, right? And that idea of giving it a particular context, like it's a hot year or a cold year, is actually what we give it when we give it a prompt. We're giving it the context that we want it to use when it's sampling from those properties. I hope that makes sense. If it didn't, then it's been a very strange 5 minutes for you to listen to. We've been talking about apples and oranges. I hope it makes sense. If not, I'll be around for the coffee later on and you can clarify with me, but there we go. So, but instead of, just to summarize, instead of learning boundaries, we're learning properties of classes and we can sample from them. Okay. Two of the things, coming forward with that idea of being able to generate new samples, and also the idea of the adaptability. So with language modeling, class I'll come to, we always knew we'd be able to create samples of text. That's what the language modeling job is. Learn the properties of language and generate new strings or sentences from language. Okay, that's what language modeling does. The large language modeling, that scalability, gives us that adaptability I spoke about before. In a sense, it means it makes them very robust to giving previous contexts that we want to sample from. All right, so we can sample lots of different questions by giving lots of different contexts. Those two things combined have been useful across a whole range of industries and a whole range of tasks. And what this diagram here is showing is a recent survey from McKinsey, okay? And they surveyed just under 3,000 companies across different regions to try and find out where those companies are using generative AI, okay? Key areas where they're using it is in the technology sector, not surprisingly, for IT support, for marketing and sales. There's a lot of work in terms of developing marketing material, but also customer interaction and management, and also product services, okay, and service development. And a key aspect of that product services and service development is in knowledge management, okay? So how do I, in order to develop my new services and products, I have a huge amount of data here. How do I analyze and structure that data? How do I manage that data? Okay, so, and I'll give some examples later of data extraction using generative AI. But those are where things are being used. Okay. So, I've been talking about this process called language modeling. All right, and given that context, I want to give you a slightly deeper understanding of what a language model is than you may have come across before. So, what is a language model? So, technically, and why is it called a language model? Why is this thing that generates text called a language model? Well, technically, a language model is a model of the probability distribution of the strings in a language. Okay? So, what that means is, if you have trained a model by making it look at a whole load of sentences from a language like English, okay? And after it's trained on that, and I'll talk to you about how that happens, later on you can say to it, okay, here's a new sentence, okay? How probable is it that that sentence occurs or is an English sentence, okay? And actually more specifically, what is the probability that this sentence I'm showing you here, this new sentence, would occur in the large data set of English that I've shown you before? Is it very likely? Is it very similar to the characteristics of what you've seen before? Or is it very different? Okay? You could imagine, for example, if I take an English sentence and I swap a couple of words to make it ungrammatical and I put it in, the probability would drop. Okay? Or if I take an English sentence about basketball, okay, and I swap out some words and randomly put other words in about fashion, okay, so you take words out of context or topics and you put them in, it's unlikely that those words would co-occur with the rest of the context, so that would drop the probability, okay. So a language model is able to look at a string and check, okay, do the words here, are they likely to co-occur together? Is the topic consistent? And is the ordering of the words that I'm seeing here similar to the ordering I would expect to see in an English sentence? And if they are, then it's a high probability, okay? If they aren't, then it's a low probability, okay? So with a language model, we can do a number of things with it. The one thing is we can give it a part of a sentence, okay, and ask it to give us a probability distribution over what's the next most likely word to come at the end of that sentence, okay? Technically there's a thing of chain rule of probability, but I won't go into that, but that's why we can go from that's just the maths behind why we can go from the probability of a full string to the probability of the components of the string, okay? And can also calculate the probability of a string of words occurring in a language. Previously, a lot of research, and why I was working with language models before, a couple of things. One is your predictive text on a phone. Okay, that's a language model. So that's been around for a long time. And actually, the first time I was working with predictive text, we were developing brain-computer interfaces for people who had locked-in syndrome and couldn't speak, and they wanted to be able to type a bit like Stephen Hawking. You know, you want to be able to predict, and you want to save those people the work of trying to pick every letter out one by one. If you can use predictive text to speed that up. But that's where one area of where language models were being worked on previously. And another area where language models had received a lot of work was in machine translation, because you can kind of break down machine translation into two tasks. One is you take the source sentence in, okay, let's say it's the English sentence. You might do a word-for-word translation into French, and then you use a language model, and those words might be in different orders, okay. You can use a language model to figure out what's the best ordering of those translated words to present in the French to make it fluent, okay. So you translate and then you sequence correctly. And the language model helps you choose which sequencing of the words will be better. Okay. So I've mentioned some of the applications that you've seen already. So you've got the predictive text. You'll have used that. You'll have used it in machine translation. Language models are a component there. But I think the thing that really made people aware of this concept of language modeling was when ChatGPT came out. So how do we train a language model? Well, we show the language model a huge amount of text from the web. We mask some of the words in the text, and then we get it to guess those missing words. All right. So, and then each time it makes a guess, if it gets the word wrong, we update the model to make it more likely that it will predict the next word or the right word in that context next time it sees it. Okay. So if I was to, basically, you can do this task. Okay. If I was to give you this string of text, we literally take text like this, mask out words, and then get the model to go along, and we say, okay, if we give you the context as part of our, okay, and then the model has to guess the next word. Anyone got a suggestion what that word might be? This is a know your customer statement. As I understand it, this is one of the most common statements you should have in business. It's part of our commitment to financial regulations and anti-money laundering. There you go. Okay. See, we've already trained a language model here. Okay. So that's the task. You go along and you get the model to guess words. If it gets it wrong, you update the model. So that's how you construct the model. We train it like that. Now, once we've trained the model in that way, the next task is that the model needs to, we want to use the model to generate text. And the way a language model generates text is you give it the context. Remember I said earlier, give me an apple when we've had a very hot year. Okay? You give it a context and you say, here's a context. Please now start generating a sample for me. Okay? So I give a language model a context in the beginning. Here's the start of a sentence. Now please generate the rest of the sentence for me. And it's going to generate that word by word. Okay? And each time it generates a word, it will add that word to the context and generate the subsequent word using that extended context. All right. Now, in a little more detail, what it's actually going to do is, at each word, you give it, at each time step in the sequence, you give it the context. What it actually does is it generates a probability distribution over all the words that it knows, which are all the words it will have seen in training. It won't know all the words in English, but it will see, like, it will know 30,000, 40,000, 50,000 words. It will generate a probability distribution over all those words, and use that probability distribution to sample the next word. Typically, it might sample the most probable word, but actually there's a trade-off there in how we sample from that probability distribution. If we always sample just the most probable word, the text can be a little bit generic, okay, and repetitive. So you can add a bit of stochasticity into how you sample, and you might have come across a term like the temperature of a language model, okay. What that means is how much randomness do we put into the sampling? Do we allow the model to choose randomly from the top 10 most frequent words or most probable words, okay? So to step through that, we start in the beginning. It generates a probability distribution over the words it knows, ranks them. In this case, we'll select the most probable one. We add that, okay? In the beginning was, then we generate the next probability, select the most likely word, the next probability distribution, select the most likely word and add it to the string, okay? And the process keeps going until it generates, the language model itself generates a word called the end of string token. We add that into the process, okay, and then it stops. The reason why I wanted to highlight that probability distribution aspect on sampling is because anytime you give it a prompt, it can generate multiple different strings for you, okay? And we sometimes use those multiple different strings and responses in training models later on, okay? And there's a big difference between the thing with language models. One is, okay, a language model can generate multiple outputs. There's a different task in terms of choosing from those outputs what's the best one to present to the user, okay? So there's generation and there's selection. There's two different components there, and that's an interesting trade-off that takes a lot of work in language models. And actually one of the big breakthroughs was figuring out how to make the selection process better. Okay, so I want to go through the development life cycle for you, and that will bring us up to that selection process. So beyond next word prediction, I've explained to you how we train a language model and how it predicts the next word. What that process does, where we give the language model lots of examples on masked words and get it to guess the missing words, is it gets the language model to understand what language looks like, okay? It allows the language model to understand what words co-occur together, all right? And allows it to mimic the text that it sees online, okay? And in a roundabout way, it gives it some indirect knowledge of what the world is, because the language we have describes the world. So it does know some things about the world in a background. Okay. What it doesn't give the model, though, is an inherent understanding of commands and intention. Okay. It doesn't make it understand words like translate, summarize, and explain. Okay. And that means that when you give it a context, if you give it an instruction as the context, it won't necessarily interpret that as an instruction. So to give you an example, and that's what we're going to do, fine-tuning, okay? So I'm going to jump forward to an example to here. If you gave a pre-trained language model the string, who wrote the novel Frankenstein, if it's just been pre-trained as we've done it so far, it might just take the context Frankenstein, okay, not understand that you're asking a question that wants the answer, who wrote it, and then just start a continuation in the general topic of Frankenstein, okay, because it has that context, all right? What we want to do, though, is to change it from that to not just continuing text under the topic, but also to understand that we have a query, that we have an intention behind, and we want an answer in response to that query, okay? So that's what fine-tuning comes about, instruction fine-tuning. So we have pre-training, and then we have instruction fine-tuning. What we do with instruction fine-tuning, the process is the exact same as previously. We're showing it examples and getting it to predict missing words from the examples. We don't change the learning process. All we change is the data that we present. So whereas in pre-training we basically take any good quality data off the web and we get it to predict the missing words in that data, in instruction fine-tuning we might have a much smaller data set, 50,000 or 100,000 examples, but each example will be an instruction followed by an answer, okay? So then it starts learning, okay, well, when the context has this word, like summarize, this is what the answer looks like. Does that make sense? So that's going from pre-training to instruction fine-tuning, all right? And those two slides are just giving you an overview of that. So what we're teaching the model here with instruction fine-tuning is how to follow instructions correctly, rather than just generate continuations that are coherent. There's a last piece then in the development life cycle, which is called reinforcement learning with human feedback. Okay? So we have our pre-trained language model. It can generate continuations. We then have an instruction-tuned language model. It can respond to requests. But when it responds to requests, the responses mightn't be exactly what we want in terms of tone, helpfulness, conciseness, etc. So remember I was saying how it might generate multiple different options as a response? Okay? It mightn't choose the right one of its options to give back to us. Okay? It might generate one very long answer and one very short answer, or maybe we prefer the shorter answer. Okay? And it mightn't present the right answer that it generates for us. So this reinforcement learning with human feedback is really helping the model to learn how to, from the set of possible strings that it generates, to re-rank them to give us the one that is best suited to what humans prefer. Okay? So training with reinforcement learning, it's also called the alignment problem, aligning the response to the human's intent. Training an LLM with RLHF helps the model to learn how to re-rank outputs generated in order to select the one that best aligns with the human preferences. Okay? I was chatting too long earlier on, so I'm a bit against time, so I'm going to move ahead forward, okay? But hopefully you've got the idea of what RLHF does and how it fits in, all right? It has a three-step process. The first part of the process is actually basically the fine-tuning stage that we just went through. That first column is fine-tuning. What we then do is, you'll notice there's a lot of human effort in the middle there, around here, because we have a human that's generating those instructions. Okay, answer pairs. The next thing is we take a prompt, we generate multiple responses from a language model in response to that prompt, and then we have a human annotator label of the responses which is the best one. And we train a model then to say, okay, if I show you these multiple responses, which is the better one to respond? Supervised learning. And then we use that model that we've trained here, the reward model, okay, which is learning, the reward is rewarding the models that rank the best responses highest. We use that model to update the language model in order to give the best responses from the ones it can generate. That's RLHF. Okay. So it's a kind of a three-step process coming through into the standard pipeline. We've got pre-training, huge amounts of data that we've just taken from the web. We normally have to do some quality assurance on it, but we mask words and learn that. Then fine-tuning, smaller amounts of data with instructions followed by responses, okay? But in both of them, we're doing the same thing, guessing missing words, given the data that we're sampling from. And then RLHF is helping the model to learn how to re-rank the different outputs it can generate. That's the overall cycle, okay? You put them all together, you end up with ChatGPT, okay? So one of the things, though, that is, I mentioned earlier how when we train a language model with pre-training, to an extent it has some knowledge of the world, just by knowing how words co-occur together. Because words are language, corresponds to the world. Well, some people's language corresponds to the world, okay? Knowing how words co-occur together implicitly gives the model knowledge of the world. That means that early on people started to use these models a little bit as a lookup system, okay? Querying the models. What's important to know, though, is that these models, while they know word co-occurrence and that, they're not databases, okay? So, and that means that their knowledge can go out of date, right? They can also do things like hallucination, which I'll talk about a little later on, okay? We have a system called retrieval augmented generation, which is a way of trying to help the model to update its knowledge in a more structured way, okay? Retrieval augmented generation, the challenges that we're looking at is we're dealing with the fact that the knowledge of the system can go out of date, and that we would like sometimes for it to be able to cite the sources that it's using when it's making an output, and we also want to reduce hallucinations. It has a number of advantages. It improves the accuracy, it helps us with fact-checking, and it's easy to update the sources. And essentially what happens in a RAG system is you put in your prompt, your query, the system looks up a database, okay, retrieves relevant content from that database, okay, and there's a number of different methods here. I happen to use them, and it uses those examples as context. Without you knowing it, it adds that context to your prompt. Okay, so you'll see your queries coming in from the left. Okay, it goes along here. We go through the database to retrieve content. This might be documents that you want. Okay, compliance regulations, they're added in. And then there's some extra instructions added at the top of the prompt, see above the query. And that would be instructions to the model like, when you're responding, use the context of the documents that I've given here as the basis for the response. Okay, don't use other examples, try not to hallucinate. And then it will generate a response for you based on those samples. Okay, so it's integrating a database system into your chat response system. Okay, and that means that if you update your database system, you can keep the language models up-to-date knowledge. All right, it means the language model itself doesn't have to be the knowledge store anymore. It's the interface that's finding out what you need and giving you the response in a natural process. That leads to the era of prompt engineering. Okay, so prompt engineering is how do we ask the questions in the right way for the system and to get the responses we want. And I want to give you 3 or 4 key things that you might want to do if you're designing prompts yourself. One is you need to be clear about the task. Okay, don't be ambiguous. Where possible, give it the output format you want. Specify the output format. And there's a thing called few-shot learning or in-context learning, which comes with scalability. Give it examples of the task if you can. And you might also see, if you're looking at prompts, statements like role framing, where somebody's telling the language model, you know, you're a helpful academic assistant, you're a helpful business analyst. The reason why you might use role framing statements is they kind of set expectations in terms of the language and tone that you want the response to come in. Okay, so that examples aspect, what I'm giving you an example here is when models become large enough, as I said earlier, they can adapt their behavior. And one way of getting to adapt their behavior is to show them the type of behavior you'd like them to follow by giving them examples of that behavior. So here we're giving them examples of reviews, okay, of movies, I think. And we say, okay, here's a review. This movie is dreadful. The sentiment was negative. Okay, so we're turning the model, a language model, into a classification system by showing it previous examples that we wanted to classify. Okay, and then we show it another review, and it gives us the output of positive. Okay, that idea of giving examples in the input or in the context to specify the behavior we want the model to follow is called in-context learning. Okay. This is just a more detailed one where I have shown a sequence of examples, okay, where we're classifying customer messages, and at the end you'll see it just identifies the last sample as a billing issue. Okay. The reason why I'm putting that example up is it is as straightforward as I'm describing it. The great thing about LLMs is because they use natural language so easily, we can all do prompt engineering to an extent. Okay. I went through a number of other examples in the next few slides. I'll go through them very quickly. One of them was just saying, okay, an example of how we can use prompt engineering to extract information from a text. Another one is to show how we use prompt engineering to summarize information from multiple documents. Okay? And actually it's very simple, the similar structure of you have role framing, define the task, and define the output format. Okay, in each case. So role framing, you're an AI assistant, I want you to extract this information and please give it to me in this JSON format. Okay? Here's the transcript I want you, this is a business transcript from a meeting, and it will give it back to me in the format I've requested. Okay, I can extend that to multiple documents. Imagine you're working in an insurance company and you get a sequence of emails from a potential client. So they contact you about insurance, they give you some information, you respond to them, ask them some questions, they come back to you, and then you ask the model to take these multiple emails, okay, and you'll notice here that sometimes if you have multiple documents, it can be good in the prompt to delimit them with, you'll see I have the email opening and closing brackets. It can be useful for the model to know there's different documents there, and ask it to extract information from multiple documents. It will give it back to me in that format as well. Okay. You can also use prompts to go from structured data to text. So I'm just trying to show some of the examples of where people can just by themselves generate prompts to try and speed up their own processes. An interesting example as well is comparing two documents. So imagine you have, here's two summaries of NDAs, and you're comparing two NDAs to extract what's the differences between them. But you could imagine comparing two contracts, and you want the model to see, well, which of these is better for me? Can you summarize the differences and save time in those? And that process actually identified on a clause-by-clause basis all of the differences between the two NDAs. Okay, hope that's readable. To give you a kind of a space of understanding where we have RAG and fine-tuning and prompt engineering, if you have your language model, okay, and you want to update its knowledge, it's good to go with RAG, okay. If you want to change its behavior, you do instruction fine-tuning to change the language style and RLHF. Okay. And then I'm going to finish up here. One thing I want to highlight is just, I'll do 2 more slides and I'll stop then. There's a range of different language models out there. You're used to ChatGPT. You've probably heard of the fact that they can generate code as well. That's simply we changed the instruction fine-tuning to have code examples in there. We've talked about RAG systems. I won't have time to go through multimodal systems, but I do want to highlight, because I think it's important for the agentic AI later on, I want to talk a little bit about reasoning models. Okay? So another phenomenon that people identified when the language models got very big is a thing called chain of thought reasoning. Okay? What that is if you gave and this is on the right-hand side, hopefully that's big enough. Okay, these two different prompts. What you'll see in the standard prompting dialogue is somebody's posing a maths question to a language model. Okay? And the language model responds, and the language model gets the answer wrong. Okay? And then what they did on the other side was they were posing the exact same prompt, okay, the language model, but in the examples they're given, and you might do it explicitly, they are prompting the language model to give its reasons for its answer. Okay? And when you ask the language model to give its reasons for its answer, it gets the answer right, the same language model. Okay, so it gets the math sum wrong when you don't ask it to reason through, and when you do ask it to reason through, it gets it right. There's a number of theoretical reasons why this might happen. One of them is that a language model has a fixed compute budget per token that it generates, and as you ask it to generate more tokens to reason, it's allowing it to use more compute in generating the response. Okay? Or you might also, actually in more sophisticated ones like DeepSeek, you can think of it as it's generating multiple outputs, okay, in the text space, and then rethinking and verifying them. Okay? But chain of thought reasoning has led to reasoning language models, because what we can do is, if we train a language model where we're doing the instruction fine-tuning, but include in the instruction fine-tuning data set the responses, we include reasoning steps, then the language model becomes tailored to thinking or reasoning through its responses rather than jumping straight to the response. That means that language models are able to take on bigger planning steps, okay, broader concepts and multi-step reasoning, okay, and that's the basis for a lot of the work around agentic AI, where you can give it, rather than having the model respond directly to one prompt, you give it a higher level goal, and it can reason through what steps it needs to do to complete that role, and then come back with a solution for you for that, okay, with a higher level autonomy. Right? I'm up against time, so I should finish there, I think, because are we, is that okay, Andy? Yeah? No? Okay. So am I okay to? Okay, I'm still good. Okay. So then, that's great, because I wanted to get on to hallucinations and bias. I didn't want to skip that bit, okay? But the reasoning models are really exciting. They're right at the core of what's happening, okay, the basis for agentic AI. There is some downsides to them, all right, and that's one of the things I want to highlight. They can sometimes overthink. Okay, now, by the way, when I say the word think here, you know, it's obviously anthropomorphizing word, okay? We can have a discussion over coffee about whether or not it's actually thinking, but it can overcompute, let's say, okay? It can spend more time checking its response than it should. And remember that each time it's generating, that is burning energy, okay? And it can also slow down the response time. There's latency issues around these problems. So reasoning models aren't suitable for all tasks, but they can be very suitable in some domains. For example, I've come across some use cases where they're used for financial analysis. But again, in all domains, you should always verify and check the response that comes back. Okay? And the reason why you should do that is because of things called hallucinations and bias. All right? So a hallucination is that while these models generate very fluent text that's very believable, they're not always accurate. They can generate, well, they can act like a human, I guess. They can say untruths, okay? So now one thing to bear in mind is that hallucinations can come in two forms. One form is the idea that the thing the language model is saying is not true with respect to our knowledge of the world. Okay? That's a natural type of hallucination. The thing it said isn't what I believe about the world. Another form of hallucination, though, is the thing that the language model is saying is not true with respect to the source documents I've asked it to analyze. Okay? Now, those two types of hallucinations are often the same, but sometimes if you're asking it to analyze a source document which has errors in it or has untruths about the world, the question is, should the model respond as in being true to the world, or should it respond as in true to the source document? If you ask it to summarize a report that you've been given, and there's an error in that report, you want it to actually say, well, this is what this report actually says, rather than fix it. Okay, so hallucinations can come in two forms with respect to which source it is that it diverges from. Does that distinction make sense to folks? Okay. So hallucinations, what can go wrong? Well, to give you an example of why this is important for business, what you're looking at here is an image of the launch of Claude, which was a Google large language model, its first big play in the AI space. And at the launch, so they were trying to come up with nice demos and examples that, you know, what's going to cause problems? Something that's a clean, business-friendly example. And the example they said was, what new discoveries from the James Webb telescope can I tell my 9-year-old child about? What can go wrong with this? Astronomy, space, 9-year-olds. And the language model generated this response. And it said, your 9-year-old child might like the following discoveries. Okay. One of the problems with this was after it went online at the launch, someone pointed out that the James Webb telescope did not take, see the last bullet point? The James Webb telescope took the very first picture of a planet outside of our own solar system. That is not true. Okay, the James Webb telescope did not do that. Okay, so that's an example of hallucination. That's an example of a fairly impactful hallucination because Google shares lost 100 billion. Okay, after the company's AI chatbot makes an error during a demo. Okay, so these are important things to pay attention to in the wrong context. Okay. What causes hallucinations? One is that the thing we're asking the model to do, okay, or talk about, the topic that we're dealing with, might be outside of what it came across in its training data. Okay, so it doesn't know what words should co-occur together. There might also be a divergence between the training data and the prompt. One of the things that we have to be careful of in our training data is we don't want to repeat the same statements multiple times. Otherwise, the model will be too focused on giving you back that data. Okay, that's called a parameterization bias. All right, and that means it might give you back that data even if the prompt is suggesting that it should give you other information. Okay, so we have to do a lot of curation on the data that we use to train the model. And I also mentioned to you earlier on those different decoding strategies, that discussion about temperature, how we sample from that probability distribution. If you give it too much stochasticity, it might make the model more creative in its responses, but it might also make it hallucinate more. There's a trade-off there. Okay. And finally, just talking about bias in generative AI, there are systems, for example, the data that we have, as I mentioned before, describes the world. And the world we live in isn't always a particularly ethical or fair or equitable world. And the language we have describes that unfair, equitable world. And that means that if we have our technologies regurgitate samples from that description of the world, it can reinforce the biases in that world. Okay? Now, I could use examples from language okay? But I think it's easier to show some of the challenges and problems that can occur from a visual perspective. And what I'm actually showing here is systems why it's so hard to get things right, okay? So for a long time there's been criticisms of some of the image data sets that these things are trained on, that all the doctors are white men, you know, criminals are from a different ethnicity, okay? And people have rightly looked to have image generation, other systems address those biases. But these are really difficult to do. So for example, what I'm showing you here is some examples of where the systems, they try to force the models to be more diverse, okay? And they put in, remember for example, I showed you in the RAG system, we can add in some extra prompts that might be hidden, not just the context, but we might say, oh, and when you're doing it, use these prompts. But you can also add in, we call these system instructions, okay? You can also add in prompts like, oh, and when you're generating this image, okay, please ensure that you generate a set of images where there's diversity in terms of ethnicity, color, gender, etc. All right? What can go wrong with that? Well, for example, if somebody asks, oh, please generate some images of medieval British kings, okay, you wouldn't expect them to necessarily look like these images on the left-hand side, all right? Or alternatively, more shockingly, if somebody asks, can you generate an image of a 1943 German soldier for me? Okay, you're not expecting that the German soldiers would be looking like women from Asia, for example. Okay, the reason what I'm trying to show you here is there are problems with bias, but they're very difficult. They can be difficult to fix. Okay, the key aspect of it is trying to get the data that goes in at the start better. There's a lot of guardrails that people are putting in, but then there's a whole area called jailbreaking, where people are trying to figure out how to get around any guardrails that you put into a system. So it's just like, anyway, that's the world. So final thoughts, I'll finish here. I think one of the challenges, so if I look around at the industry and the reports I'm reading and talking to people, companies are reporting that they're getting productivity gains, okay, from adopting generative AI systems, okay, and they're also reducing costs. That is happening. But those gains and cost reductions are related to comprehensive, systematic, strategic integration of generative AI into workflows, all right? The challenge is, though, that in a lot of places, okay, if you talk to CEOs, so for example, the McKinsey have done a survey recently, and they've spoken to a lot of industry leaders, and what most of those industry leaders say is, yes, we found this useful, but actually very few of our companies have really gotten that strategic process in place for integrating this technology into our platforms. So while we're getting some benefits, we're not getting where we need to be because we don't have the strategy behind it. So I think that's the challenge for how we integrate this technology going forward.